If you're listening to this, you're relying on a network, probably several, actually. The internet, a power grid, a social platform, and every single one of those complex systems, no matter how robust it seems, it has a hidden flaw. The single point of failure. I want you to visualize a huge network map, maybe a city's transit system. Now focus on just one hub one station, maybe one router, that if you removed it wouldn't just, cause delays, it would completely slice the network into two or more isolated islands. That is the core of what we're tackling today. We're not interested in simple connectivity, just the idea that a path exists. We want to understand true resilience. So we're diving deep into the math that finds these articulation points and maps the robust neighborhoods they connect, the bi-connected components.
Right, and before the 1970s, finding these critical nodes was, well, it was a computational nightmare.
You'd have to just break the system to test it.
Exactly. The only guaranteed way was to pull a node out and then run an expensive search across the entire rest of the network to see if it was still connected. Now imagine doing that for every single junction in a million-node grid.
You'd be waiting for centuries for the results. It's completely unfeasible. So our mission today is to understand the brilliant breakthrough by John Hopcroft and Robert Tarjan in 1973. They found a way to solve this in one elegant pass. They could analyze a system's entire resilience architecture in linear time. It was just a complete game changer. Okay, let's unpack how they pulled off this magic.
Well, to really get the breakthrough, we have to define the problem of fragility first. As you said, a graph is connected if there's a path between any 2 points. But that's a very weak guarantee, structurally. It just takes one critical node, an articulation point, to break that chain.
And then whole sections are just cut off.
Completely isolated. So biconnectivity is the gold standard we're aiming for. A structure is biconnected if it stays connected even after you remove any single vertex.
That's a high bar.
It's a very high bar. It means that for any 2 points in that system, there had to be at least two completely separate vertex disjoint paths linking them. One path fails, the other's still there.
So we're not just hunting for the weak points. We're really trying to map out the stable neighborhoods.
That's the perfect way to put it. We call these neighborhoods blocks, or maximal biconnected subgraphs. And here's a really crucial distinction for anyone learning this. The graph is partitioned based on its edges. Every single edge belongs to exactly one block.
Okay.
But the vertices, especially the articulation points, can be shared. They can belong to multiple blocks, acting like structural hinges holding the whole architecture together.
That makes perfect sense. The physical link is in one group, but the shared hub, the junction, connects all the different groups.
And we should probably mention the parallel idea of edge connectivity.
Right, where you're worried about a link failing, not a node.
Exactly. If removing a single edge, a cable, a road fragments the network, we call that edge a bridge. A bridge is, by definition, the least resilient structure possible. But for most critical infrastructure, you have to plan for the more severe case, node failure.
The bar is definitely higher for node failure. Okay, so back to the efficiency problem. That brute force method of testing every node. How did Hopcroft and Tarjan get around it? They needed a single pass method, something that could make these huge judgments about resilience using only local information.
The core idea was to use a depth-first search, a DFS, as the actual tool. When you run a standard DFS, it naturally organizes the network into a tree. Their genius was realizing that if you just record two specific temporal markers during that one search,
the tree's own geometry reveals all the vulnerabilities.
Instantly.
It's like sending a scout into a huge territory, and that scout just has to record two specific pieces of information at every single junction it finds. The first piece of info is pretty straightforward, the discovery time.
Yep, just the order in which you first visit a vertex, let's call it 2 hour. It's the absolute timeline of the search, 1, 2, 3, 4, and so on.
But the second piece, this is the key to the whole operation, right? The low link value.
This is the secret sauce. For any node, 3 days, the low link value tracks the highest, most ancient ancestor that $2 or anything beneath it in the DFS tree can reach.
Okay, so it's like a lifeline.
It is a lifeline. It's the highest point it can jump back to using its tree connections and at most one special connection.
And that special connection is the back edge.
Precisely. A back edge is when your DFS finds a connection from the current node back up to an ancestor that's already been visited. That edge closes a cycle, and cycles are the fundamental unit of resilience. They are the structural glue.
They give you a redundant path.
They do. And the low link value quantifies the strength of that glue. It tells you how far back your safety net reaches.
Here's where it gets really interesting. We have the data now, discovery time and low link. How do we actually make the call, the articulation test?
The test happens on the way back, as the DFS is unwinding. When it returns from a child, say $V to its parent, to $1, it asks a simple but profound question. It asks, can the dollar's entire subtree reach an ancestor that is higher up than its own parent $2?
So can it jump over its parent to safety?
That's it, exactly. If the answer is no, if the low link value of the child $5 is greater than or equal to the discovery time of the parent, then that parent, high dollars, is an articulation point.
Let's really zoom in on that. If the highest point that entire cluster under dollar can reach is only dollar itself, that means that dollars is the mandatory gateway. You remove two, and that entire branch of the network is just severed. The lifeline wasn't long enough.
A perfect summary. If $5 can make that jump back to an ancestor of 2, then operators is redundant. There's another way around. If it can't, dollars is critical.
And there's a special case for the root, right?
Yes, a necessary exception. The root of the DFS tree is only an articulation point if it has more than one child, because removing it then isolates those distinct branches from each other.
Okay, so we can identify the bottlenecks, but that's only half the battle. How do we find the entire robust component, the block that it's a part of? I mean, if the DFS is running in a single pass, how do you efficiently extract that whole group of nodes and edges without ruining the OV plus E efficiency?
This is where the sheer elegance of the edge stack mechanism comes in.
And why an edge stack? Why not just track the vertices?
Because we go back to that key structural truth. An articulation point can belong to many blocks, but an edge, every single edge belongs to exactly one.
So the edge stack respects that property. It keeps the accounting clean?
Perfectly clean. So as the DFS explores, every edge it crosses, tree edge going down, back edge going up, gets pushed onto a global stack.
Okay, so the stack is just accumulating the path you're on.
Right, and the magic happens when we backtrack and that articulation test is triggered. The moment the algorithm confirms that little dollars is a bottleneck for its child $V, a pop cycle begins.
And this is immediate.
Immediate. All edges are popped from the top of the stack one by one until the edge V itself is removed. And that set of edges you just popped,
That's your block.
that is a complete maximal bi-connected component. It's a real-time, on-the-fly architectural survey. Deep nested components get found and extracted first. You never revisit an edge.
That's fantastic. So we've established the Hopcroft-Tarjan DFS framework is the standard for serial performance. But there's often another way to look at these things. You mentioned ear decomposition.
Yes. If Hopcroft-Tarjan is the efficient explorer, you can think of ear decomposition as the pure structural architect. It's a different philosophy.
How does it work?
It partitions a graph into a sequence of edge disjoint paths or cycles, which are called ears. Think of it like weaving a complex knot. The first ear is a basic cycle. Then every subsequent ear is a path that starts on that existing structure, goes out, and comes back to attach at a different point.
And what does that structure tell you?
The existence of an open ear decomposition, where each new ear only attaches at its two endpoints, is basically an undeniable certificate that the graph is bi-connected.
It's a structural proof of resilience.
Exactly. So why choose one over the other? For most general-purpose work on a standard computer, the DFS stack method wins. It's fast, simple, low overhead. It just works.
But ear decomposition has its own niche.
It does. It shines in the world of massive data and supercomputing because of its parallel scalability. Because it's path-based, the process is highly adaptable to parallel processing. You can find an ear decomposition in logarithmic time on a parallel machine, which is way, way faster than a serial DFS on a giant data set.
That's fascinating. So the best tool depends on the architecture of your computer, not just the graph itself. Now, we found the blocks, we found the cut nodes. It feels like we're done, but this is actually the entry point to a higher level of analysis.
It is. This is the payoff. The block cut tree.
The BCC graph.
Exactly. It's a high-level topological map that, well, it linearizes the connectivity of your entire network.
What does that mean? It linearizes it.
Imagine taking your messy, complex network and flattening it into a simple bipartite tree. The nodes in this new map represent two things. One type of node represents the blocks, the components we just found. The other type represents the cut nodes, the articulation points.
And the edges in this new tree.
An edge just connects a block node to a cut node if that articulation point is physically part of that component.
And the advantage is that in a tree, there's only one path between any two nodes. No more cycles, no more confusion.
Phenomenal advantage. Consider a practical query. Is router C a critical bottleneck between server A and server B?
In the original graph, that's a huge pathfinding problem. It could take ages.
Right, that expensive O of V plus E cost we wanted to avoid. But in the block cut tree, the query is simple. You find the block for A, find the block for B,
And then you just check if cut node C is on the one unique path between them in the tree.
which is a trivial problem you can solve in logarithmic time, sometimes even constant time. You turn a hard graph problem into an instantaneous lookup.
That's the real power. It's not just finding the pieces, it's building a usable map from them for real-time decision making. And this analysis is just fundamental everywhere. I mean, for engineers managing a power grid, this is how they prioritize redundancy. The BCC tree flags a cut node.
That node gets a backup system.
Yeah.
Immediately.
In social networks, these are the social brokers connecting otherwise separate communities.
Right, and in supply chains, they're the single source suppliers whose failure could fragment the entire business process. The blocks are the teams that are self-sufficient.
And in software engineering, for circuit board layouts, this is essential for planarity testing, right? Making sure the electrical traces don't have to cross each other.
It is. The elegant truth here is that this one linear time stack-based DFS captures the entire resilience architecture of any network. It gives you the pieces to build that block cut tree, which lets us manage incredible complexity.
We spend so much time focusing on making the robust parts of a system, the blocks, even stronger. But the brilliance of this is that it forces you to confront your explicit weaknesses, the cut nodes. So for you, the learner, think about a complex system you interact with every day. Maybe a company's internal structure, a piece of software you rely on, a local community group. If you were to apply this analysis and build that block cut tree, which single person or junction or server would that map highlight as the system's most critical point of failure? And what necessary immediate changes would that insight demand? Thanks for diving deep with us.